Hey everyone, welcome back. In this lesson, it's actually going to be a very short lesson today. We're just going to continue the idea of related rates. The last lesson was a little bit long because we had to get through the idea of what it was, but this time it's going to be pretty short. And actually, the next three videos, including this one, are going to be pretty short because I'm just going to go over one simple example. Simple maybe is not the right word, but one example in each one of those videos. Okay, so we're just the idea is to just get more practice with related rates. And so here's kind of a method to approach these things. The first thing you're going to want to do is draw a picture of whatever's being described and identify with that picture. You want to identify what relationships are going on. Are we talking about the Pythagorean theorem? Are we talking about volume? Are we talking about trigonometry? There's a lot, or similarity. There's a lot of different relationships that we can talk about in these. So step two is to create an equation that relates all those functions of time together. Okay. Step three is to differentiate, but make sure you are using implicit differentiation and you're treating pretty much everything as a function of time or of something else. Okay. Number four is to substitute then. Remember, last time I said do not substitute until after you take the derivative, unless the thing that you're substituting is a constant value. And that's so important. So basically, remember, it's kind of like this. We're watching a movie and we're seeing things change. Seeing things move. The question that's usually being asked is, at this particular moment in time, what's taking place? Now, I can easily say at this moment in time, or at this moment in time, or at this moment in time. So you can't plug in until after you take the derivative. Now, once you take the derivative, then you are free to substitute, because remember, when you are substituting, that's essentially that's when you pause the video. Okay, that's when you freeze the video and say, okay, what's happening at this moment? And so you don't want to pause that video until after you take the derivative, so you know what's taking place there. Because if you substitute and then take the derivative, you're going to be taking the derivative of a bunch of constant values. We won't do that. Okay. And number five is interpret your results. The last video, the very last problem, I didn't really interpret what was actually happening. We could say that the hot air balloon is rising at a rate of 140 feet per minute or whatever it was. Okay. But the last thing you want to do is interpret your results. Not as in the last thing you want to do, as in don't ever do that. It's the last thing on the list that you need to do. Anyways, so here's an example. A car heads south toward an intersection at 60 miles per hour when they are 0.6 miles from the intersection. So that means their rate is changing depending on time, depending on how far they are away from the intersection. But at this moment in time, they are traveling at 60 miles per hour. If another car is 0.8 miles from the intersection heading east, and the distance between the two cars is increasing by 20 miles per hour, how fast is the second car traveling? So we have a bunch of information there. The first thing we're going to want to do is draw a picture. So it says a car is heading south. So let's say that this is the car, and it's heading south toward an intersection. So let's say at this point is the intersection. Okay, so this is my intersection, and this is the car that's heading south. We have another car that is heading east, and it says from the intersection. So they're at the intersection and they're heading east. So you can see what's happening here. You have one car that's getting closer to the intersection, and one car that's getting further away from the intersection, going in a different direction. Okay. Now, based on this is the guy heading east, I guess you can say. Let's identify all the pieces we have. Now, I don't want to put it in the picture. I want to list it off to the side, because again, if I put it in the picture, I'm implying that it's not changing, it's a constant, and that's not necessarily true. The car heading south is traveling at a rate of 60 miles per hour. Well, that's a rate, so that's going to be ds dt is 60 miles per hour. But the thing that you have to be careful of is, remember the relationships. If a function is increasing, then its derivative is positive. If a function is decreasing, then its derivative is negative. In other words, let me rephrase that. If a distance is increasing, then its rate is positive. If the distance is increasing, then the rate is positive. If the distance is decreasing, then the rate is negative. Okay? We are saying that this car is heading south toward the intersection at a rate of 60 miles per hour. But notice this distance between the car heading south and the intersection is decreasing. If it were to pass the intersection, the moment it passes the intersection, we would then say that the rate is positive because the distance between it and the intersection is increasing. If he was heading north instead of south, then this would be a positive 60 because the distance is increasing. But because he's heading south, we're going to put a negative 60 there because that length is decreasing. That's important. All right, so that it tells us that. What else does it tell us? It says if another car, and then it says when they are 0.6 miles away. So when S is 0.6 miles away, not negative 0.6 because that's a distance. How far is it away? It's 0.6. Then it says if another car, the eastbound car, is 0.8 miles from the intersection, so that would be east. E is 0.8. That car is 0.8 miles away from the intersection, heading east, and the distance between the two cars is increasing. The distance between the two cars is this length here. Okay? That is our distance between the two cars. We'll call that D. It says that the distance is increasing, which means its derivative is positive. So we would say dd dt is positive 20 miles per hour. Okay. And what else does it have here? It says, how fast is the second car traveling? The second car was this car. How fast was he traveling? So the question is, how fast is he going? How fast? What is the rate? Now, how fast is it traveling? That's a speed question. But remember, speed is the absolute value of velocity. So we have to find velocity first and then answer the question. So here's all the givens, and here's the question. Now we need to create an equation that relates all of these things. Well, we're given this length, and instead of putting S up here, I'm going to say S is here, and E is here because that's the distance between them. What's the equation that relates all three of these things in static time, or static motion? That would be S squared plus E squared equals D squared. The Pythagorean theorem, if we're talking about an intersection, generally speaking, they are right angles, so the Pythagorean theorem works. Now we need to take the derivative in respect to time. So we would say 2s times s prime plus 2e times e prime equals 2d times d prime. Okay, and I don't want to mix up my notation, so I'm going to go ahead and change this to Leibniz notation. So 2s times ds dt plus 2e times de dt equals 2d times dd dt. Now we can go ahead and plug things in. We got a bunch of information. We know what S is. We know what ds dt is. We know what E is. We don't know what de dt is. This is my variable. This is the thing I want to solve for. D, we don't know D. And we do know D. Oh, that's an R. T, I should say. Okay. So we need to figure out what D is so that we can substitute that in. Well, at the moment where I freeze the film, I pause the video, I know that these two things are true at the moment I pause the video. So now I can look at it in terms of a basic equation at that point in time. We could say 0.6 squared plus 0.8 squared equals d squared. And you guys should recognize these as 3, 4, 5 triangles, but if you don't, that'd be 3.6 plus 6.4 equals d squared. That'd be 10 equals d squared. Yeah. And then the square root of that is, sorry, I have that wrong. 0.6 squared. Welcome to math. 0.36 and 0.64. I was going to say that doesn't work out. Okay, so we get d equals 1, or d squared equals 1. So that means d equals 1. D equals 1 at this moment in time. So now I have all the information I need to plug in. So it's going to be 2 times 0.6 times negative 60 plus 2 times 0.8 times I don't know, that's what the question is, equals 2 times 1 times 20. And then simplifying that, that's, what is that? That's 360, 36, negative 18 plus 1.6 dE dt equals 40. So we've got 58 equals 1.6 dE dt. And then divide by 1.6. So dE dt equals whatever that is. Let me grab a calculator here. 58 divided by 1.6 is going to be 36.25. I'm going to go ahead and verify to make sure I'm right, because I did not look at this before we started. Those are my given informations. There's my Pythagorean theorem. Implicit differentiation. Got to figure out that hypotenuse length so I can plug it back in. And, whoa, what's going on here? That's, what in the world did I do wrong? Let's see, 20.6, 1.8, 72. Where did I get? Oh, yeah, that's way off. Negative 18. What? Oh, I was doing 1/2, not times 2. Wow. 36, that'd be 72. So that would be, that's going to end up being negative 72. So that's going to end up being 112. And then as a result of that, we end up with 70. Wow, that's pretty bad. That is really bad. Okay, so here we have our answer. The last thing we want to do is interpret our results. We know that dE dt is 70. Well, what does that mean? That means the rate at which the car heading east is traveling at this particular moment in time is 70 miles per hour, okay? So the car is traveling east at a rate of 70 miles per hour. Now, what happens if the answer was negative 70, right? Well, we wouldn't say the car is traveling east at a rate of negative 70 miles per hour. If he was traveling at a rate that's negative, that means he was heading east, but he's traveling at a negative rate. So that means he's actually traveling west. So he's facing east, but he's moving backwards, right? So you got to be careful with this. He would actually be heading west at a rate of 70 miles per hour, right? Because positive implies that this length is increasing. If the derivative is negative, that means the distance is decreasing there. So that is our final answer. Okay. Now, with that said, that's it. I just wanted to cover one example of related rates. So hopefully, the main thing I wanted you to see out of this is the interpretation and understanding the idea of positive and negative rates. If you get a negative rate, that means you're actually heading the other way, right? And so with that said, if you have any questions on this particular problem, please comment below. Otherwise, you can have a wonderful day knowing just a little bit more about calculus.